implicit differentiation, so at least the introduction to it. My assumption is that you are in calculus and you're kind of going in for the first time and going over derivatives. You have studied them, so you know all the rules. So for the product rule, quotient rules, chain rules, and so on. And this particular topic, so the implicit differentiation, isn't really necessarily covered for calculus in a kind of a grade 12 level, but depending on your teacher, he or she may actually go into it, and I hope that they actually do so. So it's a pretty simple topic in terms of application, but it's very odd for any student to get into it because you are so used to taking derivatives of just regular functions. And those functions are kind of stemming from possible relationships between inputs and outputs, so your dependent and independent variables. And your function typically happens, okay, the way that it's defined, is defined on the left-hand side. You might have a particular function, let's say f of x is equal to, and then on the right-hand side, you provide what that function is, so what the relationship is. And now, because they're functions, most of them are extremely well defined, especially the ones that you do study in grade 12 calculus. Now, implicit differentiation is a slightly different nudge on taking derivatives when you do have multiple variables. And you certainly do use that concept quite heavily if you carry on into calculus in the future and maybe applications of calculus. So I think it's wise to be able to introduce you as a student to implicit differentiation. I don't know where you might possibly go. I'm going to cover several examples. So I'll do, for instance, these examples and take the implicit differentiation, the ones that you see right here. So you have dy dx, dz dx, dA dx, okay, of all of these different relationships between kind of left-hand side and right-hand side and the variables that are playing a role there. Now, these ones aren't super difficult, but for someone who's starting off in calculus in grade 12, they will be strange for you to do. And I'll kind of talk about what is the first inclination that a student wants to do because of the items that they've studied in the past with functions and even relationships. So they typically will want to be able to isolate for a variable first and then take the derivative. And I'll show you that you don't have to do that with implicit differentiation. You can just go straight at derivatives if you are comfortable in differentiating with respect to different variables. I'll also give you an application. So this particular application will be finding a particular equation, and notice that we have a circle here. So we will be using implicit differentiation to actually do this. So I'll show you how that works, and we'll try to plot it as well. So that's going to be the goal that we want to be able to do and the types of examples we want to get ourselves into. And hopefully that will indeed introduce you to this topic of implicit differentiation. So I want to take a step backwards first and talk about the chain rule, because if you understand the chain rule, implicit differentiation is a nice extension of that particular chain rule. So if you recall, if you had, so maybe a function, so f had x, and that function was actually made up of two functions. So we have one particular function, so let's say function 1, and it engulfs another function. So let's say function 2 is the actual input to the function. Now, so an example of this that I want to give you so that I can kind of walk you through this as well and remind you of the chain rule is, for instance, what if we have a sine function and then the argument to the sine function is something like maybe 3x squared. And that would have been our actual function, so f at x, and we wanted to be able to take the full derivative of this. Now, recall that for the chain rule, what we would do is, this really is just kind of the chain between, it's not a product of function, right, that we have. We kind of have composite functions, two things happening in here. So we have, so 1 is we have a sine function, and that sine function, I'll put a dot here, so that's the input, maybe let's say sine of x. And then we have another function as the argument. So that particular dot that you see there is the other function, 3x squared. And it is being, okay, inputted as the argument. And you may recall from the chain rule, so if I would go back into that original right here, so the composite functions definition, if I wanted to take the derivative now of the entire thing, what I would do is I would take the derivative of the first function with the argument, okay, that I would have. I have to kind of be careful here. I don't want to write this in incorrectly. So I would have this argument in here, but then I would have to multiply this, right? I would have to multiply it by the derivative of this. So this would have to be multiplied by the derivative of the actual argument of the function. And if you applied it to this sine of 3x squared, then what we would have is my f1, okay, so the derivative, okay, of that really is, well, the derivative of sine is cos, so that's going to be the cos of whatever is inside, so in this case it's the 3x squared, but then I would have to take the derivative of that argument, right? So that particular argument, which would have been f2, okay, now taking the derivative of that, so that is just 3x squared, which would have been really equal to just 6x as the derivative. And in total, my entire derivative is cos of the actual argument multiplied by 6x. And that just comes from the chain rule, right? So you have kind of studied that. I can put up a link up above that into the chain rule and applying that particular concept if you like. Now, if you come to this and you understand the chain rule, okay, directly, then doing implicit differentiation kind of from the basics and then continuing on has the same idea. So here is the idea, and I'll try my best to explain this for you. So let me put an extra page here so that it gives me enough room. So that was the chain rule déjà vu. And now let's imagine, so instead of writing functions, which we kind of have on the left-hand side, f of x equals to something, right? Now we could have, of course, written it like this. Y is equal to, and then you can write the actual function. So in this case, it was sine 3x squared. Now this would have been known as a relationship, right? So relationship between your output y and then your input, okay? And then your input is just simply your x. So we have a relationship between the two. And from here, it would have been the same derivative. The only thing is that we would have written it out as, so for example, dy dx, so we're taking the derivative with respect to x of this, and that would have been just cos of 3x squared multiplied by 6x. So far it's the same. Now, the difference is the way that we written out this. We set it up as a relation, right, in between. But it's still, this y that I have is on the left-hand side and everything else is on the right-hand side. Now, if I just kind of skip away from relations and skip away from functions altogether, and then I said, okay, well, what if I wanted to start taking the derivatives of just variables? So what if it was, okay, something like this? What if I gave you an example, and this is not a relationship because it's not going to have an equal sign, so it won't be a function either, so there's nothing like that. It's not an equality. But what if I gave you just, let's say, 3y? But I told you that the y was dependent, right? So it was dependent, okay, on x. Now, we don't know what that dependence might be. Now, we have in calculus, so as you've gone through, we've made the dependence very clear, like we could find out what that function is. But let's imagine that we don't know what that function is. We just know that y depends on x. And now, what if somebody said, well, please take the derivative of this? Now, of course, you might say, well, it's not a relation, right? It's not a function. this is really just a term, right, that I have. It's just 3y. So I would want you to kind of let go of your past for a moment and think, well, if I was going to take the derivative of this, right, I could imagine doing something like this. Okay, so let me take the derivative, right, with respect to, and this is going to be now y. So I'm going to take the derivative with respect to y of whatever this right here is. So in our case, it is just 3y. Now, if I took the derivative of that, what that would be is, now think back, because now I'm doing it with respect to y. So this would have been just 3, right? 3y, the derivative, is just 3. But if we are told that it is dependent on x, that y is dependent on x, then this is the derivative of the 3y, but we would have to multiply this like we would in the chain rule, right, of what is inside of that y. Now, that y is dependent on x. So that means that we would say, okay, so this is multiplied by dy dx. And that is now the derivative of the 3y, okay, if it is dependent on x. Now let me give you a few examples and let's continue with this pattern, hopefully that you get a little bit of a better understanding as well as we continue. So if I give you another example, right, and I would say, all right, now what if I have y, to the 4th plus 3? And now I wanted to take the derivative. And again, I'm believing that my y is dependent on x. So what I would do is, first, I have to take the derivative. So I would take the derivative of this with respect to y. And then I would have to multiply by, kind of like the chain rule, by dy dx. Now, I don't know what that dependence is, so the best that I can do is this right here. That's what I would have. That's all that I can possibly do. And now, if I did that derivative right here, then this would have been, all right, so this, the derivative of that is 4y to the 3 plus 3. That's a constant, so the derivative is 0. So all of this would have been now also multiplied by dy dx. Or sometimes, you might just write it like this if you are referring to that. So that's what we would have. And now if I go back to the chain rule right here, if we knew, all right, so if I knew this, right, and I was trying to take the derivative, I'm going to copy this. We knew what this was, right? So if I had the same thing, but instead somebody told me that, okay, wait a minute, I don't know what that argument is. And I'm going to call that argument y. Now that y is dependent on the x. So you would have said, okay, well, the derivative of this, so if I took the derivative, that would have been, and I applied the chain rule, I would have said the derivative of sine is cos of whatever the argument is, multiplied by whatever that argument is, that derivative, right? So I would have needed to know what that derivative is. So dy dx. Now, because I don't know what it is, I just have to leave it as dy dx. Now, for us, we knew that this was 3x squared. So it's like someone said y was equal to 3x squared. And if that's the case, then indeed, we would have just said, okay, well, let's substitute that in. That's going to be cos of 3x squared times, and now this derivative, dy dx, because I'm just applying the chain rule, really, now, hey, I can do that because now I know what that function is, meaning what the relation is between y and the actual x. It's 3x squared. So, well, that would have just told me that this is just 6x. So the chain rule assumed that we knew all of these. We knew what the composite functions were. But you don't always know that. And I know that being in grade 12, you say, well, if I don't know it, why do I need to take it? There are reasons why we have it, okay? And why we actually want to learn this thing which we call implicit differentiation. So we're implicitly differentiating just with respect to whatever variable we have. And then if that variable is dependent on something, okay, like x, then we can continue and find the full derivatives. So I hope this, introduction kind of makes sense to you. And I'll give you, another one, okay, in terms of a final kind of example, because I don't want you to think that it's just y and it's just x, continuously playing a role. What if it wasn't y? Like, what if I had, maybe it was a, and here it was squared, okay, and then it was maybe minus a. And someone said, okay, well, what would be the implicit differentiation of this if that a now depended on x? So what you would have to do is you would have to take the derivative of this. So that would have been 2a minus 1. And all of that, again, by kind of the chain rule, you would have to multiply by the derivative of the dA, but now that has to be with respect to x, because if it was dependent on x, or somebody said it's dependent on a different variable, y, or maybe b, or z, or z, whatever. So that's the idea. You basically are using the concept of the chain rule of taking derivatives and then multiplying it because your variable may be actually dependent on something else. And that's what we want to be able to use. Let's see a few examples in here like this. So here's my first. Now it says we want to use implicit differentiation. This first one that I have for you, we don't really need implicit differentiation. So here we want to be able to find dy dx, right? So the derivative with respect to x of this. Now the way that it's set up, we could say, well, I have my y in here, so I can, and this is what typically students will do, and this is what I did as well, because I was just so used to derivatives and relations with having my variable, my dependent variable on the left and everything else, my independent variable on the right, and setting up functions that way. But as you can see here, that's not the case. I have a y and an x on the left-hand side, and I have an x on the right-hand side. And the first thing, if someone said find the dy dx, what I would do as a student is I would say, okay, let me solve or isolate for y. So I would have done something like this. 3y is equal to 4x squared plus 8x. And then I would divide by the 3, so I would get just y is equal to, and this would have been 4 over 3, x squared plus 8x over 3, and it's just dividing by 3. And I would say, all right, now I have a relationships between y and my x's on the right-hand side, and this now looks very familiar to me. And I would say, okay, so my whole derivative right here, if I wanted to solve for it, would be simply, well, that's pretty easy. So 2, that's going to be 8 over 3x, that's what I have there, plus, and, well, notice we're going to get another 8 over 3 right here, and that would have been my derivative, so that's my dy dx. There's nothing wrong with that, right? You can of course isolate, but the thing is that you won't be always capable of isolating. You will have items where it is actually much easier for you to do implicit differentiation to solve this. So that's our derivative if we isolated first and then we took the derivative, if we're capable of doing that. Now, let me just show you to do exactly the same thing, but by implicit differentiation. So I'm going to take that first term, that 3y, and differentiate it. Now, first, I have to take the derivative of the 3y, which is going to be 3. And then I have to multiply it by dy dx. That's just by the chain rule, because I'm assuming that the y is dependent on the x. So that's my first item that I do. Now, my second term, Now this one is already just dependent on x, so I can just take the derivative directly. So that's going to be minus 8. That's already with respect to x. And then on the right-hand side, I would get 8. And, okay, so notice I'm taking the derivative of all of this would have been just x. And again, it's only dependent on x there. So now I can rearrange this. So sure, I can bring this over. This is going to be 8x. Notice plus 8. And then this 3, I'm going to divide both sides by it. So I'm going to get dy dx. Dividing it, okay, notice, gives me exactly the same thing. So I have been capable of using implicit differentiation to actually find out my derivative. And it's just using a chain rule, okay, with a little bit of an extra item to think about. Now, most of the time, we actually wouldn't even necessarily use this. I mean, if we're capable of isolating, great, but we're not always capable of isolating, so we maybe would have left it like this in some circumstances. And that would have been the derivative, okay, in terms of using implicit differentiation of that first equation that we had. So I hope that makes sense to you. It's going to be a little bit of a change because implicit differentiation is a little bit different than what you have been doing over and over and over in taking derivatives. But hope that you trust, okay, in me, that if you do continue, you might use implicit differentiation. Okay, quite often it leads into things called partial differentiation, so partial differential equations and so on, but that's much, much later. That won't be in grade 12 calculus unless your teacher is extremely ambitious or maybe gives you some kind of a project. So here is the other example, okay, that I have for you. So here's my second one. Okay, I'm going to take this, I'm going to copy it, I'm going to bring it down for myself, and I'll put an extra page again, just so that I can have some space. So in this example, I'm not going to be, okay, notice they're asking me to find dz dx, so I'm supposed to differentiate with respect to x. Okay, this equation, I'm not going to be isolating. I can, because there's a z, so I can move everything to one side. I'm just going to use direct, straight differentiation. So differentiate this with respect to x, that's 14. Okay, differentiate this with respect to x. That means I have to first differentiate the variable itself with respect to itself, so with respect to z. So the derivative of this, okay, with respect to z would have been 4z. But then I have to multiply. So again, kind of like chain rule, this is going to be by dz, okay, dx. And then now the derivative of this, well, that's just a constant, so it's 0. So that falls off. And now notice that if I do want this particular derivative, so dz dx, I can certainly move this over. And what you're going to find that dz dx is, 14 all over 4z. And that is interesting because you have now found the derivative, okay, with respect to x. But notice that it has a variable z in it. And that is now the difference, okay, in all the other cases that you had. So there's nothing wrong with this. You, of course, would now have restrictions. We can't really have kind of z is equal to 0 there because that would have been undefined. It would have blown up on us, that particular derivative. But this is pretty neat to be able to see that. But that's all. That would have been the implicit differentiation of this particular equation that you would have. Now, the last one, which is a very interesting one, and one that you will use if you get into trying to figure out, I'm going to actually have a video on that as well, okay, if you're trying to figure out derivatives of logs, but that's maybe for another video. So for here, let's try to see what we're going to do. Okay, so we're going to have dA dx. Okay, so on the left-hand side, so we have to take the derivative of this. All right, so taking the derivative of this, just assume that it's first with respect to a. Well, the derivative of e to the 4a, so that's going to be e to the 4a, right? So that's just derivative of a exponential. I'll put up a link up above there. Okay, so we have that times, okay, now notice we're going to have, because it's now derivative of this, so I have to do the chain rule, so this is going to be just 4 right there, and multiplied by dA over dx. Okay, so this right here is just the derivative of e to the 4a with respect to dA, okay, times, okay, dA over dx, right? So that is kind of the implicit differentiation that we need. And now on the right-hand side, well, there's not much to do. This is just simply 2. So that is pretty neat, okay, to be able to do that. So this is going to be that. And now, so let me just bring this down right here. So this is going to be 4e to the 4a times dA over dx is equal to 2. And now this particular 4, right? So we can certainly bring it on over the other side. But if you've noticed, actually, e to the 4a, and this is what we sometimes use in implicit differentiation, if you go back to the original equation right here, well, e to the 4a was just equal to 2x. So this is pretty neat. What this is telling me, this is just 4 times, this is 2x times, okay, and I'm going to write this as kind of a prime, so that's the derivative, the same thing. And that is what we have. And hey, wait a minute. Well, this now falls off pretty nicely, right? So the 2, and I guess the 2 cancels. So this is really going to be just simply, okay, 1 over 4x if you do that derivative within there. So that's pretty interesting. And I just used implicit differentiation in order to find it. So that is one great example that you would have, okay, within here. So I've done several implicit differentiations here in the introduction to it. And I pointed out in the beginning, you know, I wanted to also do this example. But I'm going to do that example in kind of a separate video so it doesn't make this one too long. And what I'll do is I'll link that one up, okay, to this one. So this is a great, okay, kind of a test for yourself and understanding implicit differentiation. And it actually relates back to a circle, which we can take derivatives of a circle. But if you recall, a circle is not a function, right? It fails the vertical test. There's multiple points, okay, on the vertical test line, which we can't have for a function. So this is really just a relation, but yet we can still find the derivatives at every point of the circle. Well, except I guess 2, which are going to be the undefined, right? Because you're going to have vertical lines. So if you are interested in that, you can go to that particular link. That's all that I'm going to say in this implicit differentiation introduction. If you like, you can put some comments, you know, hit a like, okay? And hopefully we're going to have you join our 1M journey. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.